According to the National Electrical Code, motors rated 1/8 horsepower or larger must be protected against both thermal and current overloads. Commonly used overload devices for motors include thermal overload relays, current overload relays, and combination thermal current overload relays. Thermal overload relays used by metallic strips that expand or contract with heat. They trip the circuit when the motor temperature rises too high. Current overload relays use electromagnetic coils that trip the circuit when the current exceeds a predetermined level. Combination thermal current overload relays combine the functions of both thermal overload relays and current overload relays. For motors with low amperages such as 1/4 horsepower, it may be difficult to find suitable internal overload protectors. However, there are a few options available. Firstly, Click's 950 or 970 series thermal protectors may be suitable for 1/4 horsepower motors. Secondly, Elmo's FR101 series current-only protectors are also designed for low current applications. Using single-phase thermal protectors in each of the three phases is not recommended because of phase imbalance. Single-phase thermal protectors may not trip evenly in the event of a thermal overload, potentially leading to motor damage. They also provide reduced protection. Single-phase thermal protectors provide less protection than three-phase thermal protectors, as they cannot detect phase imbalances or ground faults. Additional considerations include motor manufacturer recommendations. Consult with the motor manufacturer for their specific recommendations on overload protection. Ambient temperature should be considered. The ambient temperature where the motor will be operating must be considered when selecting overload protectors. The motor's duty cycle can affect the type of overload protection required. The cost of overload protection devices should be factored into the design decision. For specific NEC requirements, refer to NEC Section 430.32, which covers continuous duty motors more than 1 horsepower. This section states that an overload shall be selected to not exceed 125% of the motor's full load current rating for motors with a service factor of not less than 1.15, motors with a temperature rise not over 40 degrees Celsius, or motors that are marked. Overload should not exceed 115% of the motor's full load current rating for all other motors. For motors with a horsepower of 1 or less and automatically started, they must have overload protection compliant with 430.32. Additionally, they can be protected by impedance protection as described in 430.32 subsection C paragraph 2. Part 3 of Article 430 covers overload protection. 430.34 states that where the values specified for motor overload protection in 430.32 are not sufficient to start or carry the load, the next highest standard overload relay shall be permitted, provided the trip current of the overload relay does not exceed 140% of the motor full load current rating for motors with a service factor not less than 1.15 or a temperature rise not over 40 degrees Celsius. For all other motors, the trip current of the overload relay shall not exceed 130% of the motor full load current rating. If the overload relay is not sufficient to start the motor, you can increase the trip setting, but there are limits. The NEC provides guidance on the selection and sizing of these overload devices to ensure adequate protection without causing nuisance tripping. For thermal overload relays, consider inverse time characteristics, which means the relay trips faster with higher overloads. This matches the thermal characteristics of the motor. Current overload relays respond almost instantaneously to overcurrent conditions. Consider the motor's starting current when selecting the current overload relay. The relay should be able to withstand the inrush current during starting without tripping. Combination thermal current overload relays offer a balance of both types of protection, providing comprehensive motor protection. When selecting overload protection, consider the specific application and operating conditions. Factors such as ambient temperature, duty cycle, and load characteristics should be taken into account. Ambient temperature affects the thermal characteristics of the overload relay. High ambient temperatures can cause the relay to trip prematurely. Duty cycle refers to the percentage of time the motor is operating versus the percentage of time it is idle. Motors with high duty cycles require more robust overload protection. Load characteristics, such as constant torque or variable torque, can affect the type of overload protection required. Motors with constant torque loads require more sensitive overload protection. For low amperage motors, consider using solid-state overload relays. Solid-state overload relays offer precise and adjustable protection for low current applications. They provide accurate current sensing and tripping characteristics. When using single-phase thermal protectors, ensure that they are properly sized and installed. Each phase should be protected with a thermal protector that is rated for the motor's full load current. Single phasing occurs when one of the three phases is lost, causing the motor to draw excessive current. This can lead to motor overheating and failure. Ensure that the overload protection is capable of detecting and responding to single phasing conditions. Ground faults occur when there is an insulation breakdown in the motor windings, causing current to flow to ground. This can be a safety hazard and can damage the motor. Ensure that the overload protection includes ground fault protection. Coordination of overload protection with upstream protection devices is important. The overload protection should trip before any upstream protection devices, such as circuit breakers or fuses, operate. This prevents unnecessary shutdowns of the entire system. Regularly inspect and test the overload protection devices to ensure that they are functioning properly. Overload relays can drift over time, so it is important to periodically calibrate them. Keep records of all overload protection settings and maintenance activities. This information can be helpful for troubleshooting and future maintenance. Consult with a qualified electrician or engineer for assistance with selecting and installing motor overload protection. They can provide guidance on the specific requirements for your application. Motor protection is not just about overload. Short circuit protection is equally vital. While overload protection guards against sustained overcurrent, short circuit protection is designed to rapidly interrupt very high currents resulting from faults within the motor or its wiring. Fuses and circuit breakers are the primary means of providing short circuit protection. These devices are selected to interrupt fault currents that are many times the motor's full load current. The NEC specifies the maximum allowable size for fuses and circuit breakers used for motor short circuit protection. These values are based on the motor's full load current and code letter designation. The code letter indicates the motor's locked rotor current, which is the current drawn when the motor is initially started. For inverse time circuit breakers, the NEC permits an instantaneous trip setting that is adjustable. This allows the breaker to trip quickly on high fault currents while avoiding nuisance tripping on motor starting currents. Fuses offer simple and reliable short circuit protection. They are available in a variety of types, including time delay fuses and current limiting fuses. Time delay fuses can withstand temporary overloads, such as motor starting currents, without tripping. Current limiting fuses are designed to rapidly interrupt high fault currents, limiting the amount of energy released into the circuit. Motor controllers play a crucial role in starting, stopping, and protecting motors. They typically include overload relays, short circuit protection, and other control devices. Motor starters are electromechanical devices that use contacts to switch power to the motor. They are available in a variety of types, including across-the-line starters, reduced voltage starters, and solid-state starters. Across-the-line starters apply full voltage to the motor windings during starting. This provides high starting torque but also draws high inrush current. Reduced voltage starters reduce the voltage applied to the motor during starting. This reduces the inrush current but also reduces the starting torque. Solid-state starters use electronic components to control the voltage and current applied to the motor during starting. They offer smooth, stepless starting and stopping, and can also provide energy savings. Variable frequency drives, or volts, are used to control the speed and torque of motors. They convert incoming AC power to DC power and then invert it back to AC power at a variable frequency and voltage. This allows for precise control of the motor's speed and torque, and can also provide energy savings. Motor enclosures protect the motor from the environment and provide a safe place to terminate wiring. They are available in a variety of types, including open drip-proof, totally enclosed fan-cooled, and explosion-proof. Open drip-proof enclosures protect the motor from falling water and dirt. Totally enclosed fan-cooled enclosures protect the motor from dust, moisture, and corrosive atmospheres. Explosion-proof enclosures are designed to contain an internal explosion without igniting the surrounding atmosphere. Grounding is essential for motor safety. It provides a path for fault current to flow back to the source, tripping the overcurrent protection device and preventing electrical shock. Motor frames, enclosures, and conduit systems must be properly grounded. Ground fault circuit interrupters, or GFCIs, are used to protect personnel from electrical shock. They detect small imbalances in current between the hot and neutral conductors and trip the circuit if a ground fault is detected. GFCIs are required in many areas, such as bathrooms, kitchens, and outdoor locations. Surge protection devices, or SPDs, protect motors from voltage surges caused by lightning strikes, power grid switching, and other events. They divert the surge current to ground, preventing damage to the motor windings. Power quality is an important factor in motor performance and reliability. Voltage sags, swells, and harmonics can all negatively affect motor operation. Voltage sags can cause motors to stall, while voltage swells can damage motor windings. Harmonics can cause motors to overheat and vibrate. Monitoring motor performance is essential for preventing failures and optimizing energy efficiency. Motor monitoring systems can track parameters such as voltage, current, temperature, and vibration. This data can be used to detect potential problems early on, allowing for proactive maintenance. Energy-efficient motors can save significant amounts of energy over their lifespan. They are designed with improved materials and manufacturing processes to reduce losses and improve efficiency. Replacing older, less efficient motors with energy-efficient motors can result in substantial cost savings. Proper motor maintenance is essential for ensuring long life and reliable operation. Regular maintenance tasks include cleaning the motor, lubricating bearings, and inspecting wiring. Overheating is a common cause of motor failure. It can be caused by overloading, poor ventilation, or high ambient temperatures. Ensure that the motor is properly sized for the application and that it has adequate ventilation. Vibration can also cause motor failure. It can be caused by imbalanced misalignment or loose components. Regularly inspect the motor for vibration and take corrective action as needed. Motor bearings are a critical component of the motor. They support the rotor and allow it to rotate smoothly. Regularly lubricate the bearings to prevent wear and failure. Winding insulation is another critical component of the motor. It insulates the motor windings from each other and from ground. Regularly inspect the insulation for damage and replace the motor if necessary. When troubleshooting motor problems, start by checking the power supply. Ensure that the voltage and frequency are correct and that there are no voltage sags or swells. Then check the motor connections. Ensure that the wiring is properly connected and that there are no loose connections. Next, check the overload protection. Ensure that the overload relay is properly sized and that it is not tripped. If the motor still does not start, check the motor windings for continuity and resistance. If the windings are open or shorted, the motor will need to be replaced. Remember to always disconnect power before working on a motor. Electrical safety is paramount when dealing with motors. If you are not comfortable working with electricity, consult with a qualified electrician. Adhering to these guidelines helps to ensure the reliable and safe operation of motors in various applications.